In 2024, a team pointing the James Webb Space Telescope at one of the most distant galaxies we know noticed something odd. Not in the galaxy, just outside it. A faint smudge of light, 3,000 parsecs off to one side, giving off a signal that nothing ordinary should be able to produce. They spent 2 years trying to explain it away. Every explanation they reached for failed. And the thing they were left with is something astronomers have been predicting for 60 years and have never once seen. A population 3 star, the first generation, the ones that came before everything else. Nobody has ever confirmed one. So let's go through the evidence the way they did and see whether you land where they landed. Start with what they were hoping to find, because it explains why they were so careful. When the universe began, it made almost nothing. Hydrogen, helium, and a trace of lithium. And that's the entire ingredient list. No carbon, no oxygen, no iron. Every heavier element in existence, the calcium in your bones, the iron in your blood, was manufactured later, inside stars. Which means the very first generation of stars had to be built out of hydrogen and helium alone. That first generation, population 3, should have been unlike anything burning today. Without heavier elements, a collapsing gas cloud struggles to cool down, and a cloud that cannot cool cannot break into small pieces. So instead of fragmenting into many ordinary stars, it collapses into a few enormous ones, possibly hundreds of times the mass of the Sun. Monsters. And monsters die young. They would have burned for a couple of million years, exploded, and seeded the universe with the first heavy elements. That's the problem. They destroy the evidence of themselves. The moment they explode, the gas around them is no longer pristine, and any stars that form next are already contaminated. 60 years of theory, and not one confirmed observation. Now the object. GN-Z11 is one of the brightest galaxies we've ever found in the early universe, sitting at a redshift of 10.6, which means we're seeing it as it was roughly 400 million years after the Big Bang. It's been studied intensely, and it's not pristine. Its spectrum is full of heavy elements. Whatever made the first stars, GN-Z11 itself is well past that stage. But in 2024, using an instrument on Webb that takes a spectrum of every point in an image at once, Roberto Maiolino's team found a faint emission line coming from a small companion object beside it, since named Hebe. And the line was helium. Not ordinary helium, doubly ionized helium, meaning helium atoms stripped of both their electrons. That detail is the whole case, so it's worth being clear about it. Tearing both electrons of a helium atom takes brutally energetic ultraviolet light, far more energetic than an ordinary star produces. Something next to that galaxy was radiating hard enough to strip helium bare. The question was what? And when they went back with the instrument set to high resolution, the line did something else. It split. What looked like one emission line resolved into two distinct components, separated by about 120 kilometers per second. Two things inside that small clump moving relative to each other. The strength of the line held up to an equivalent width above 20 angstroms, which means whatever is producing it is doing so with real efficiency, not marginally. Here's where it becomes an investigation, because a strong helium signal on its own is not proof of anything. Several things in the universe can produce it, and each had to be eliminated. The first suspect is an accreting black hole. Gas spiraling into a black hole gets hot enough to emit that kind of radiation. So this would be the boring answer. But a feeding black hole is loud in other ways. It produces a characteristic spread of other emission lines alongside the helium, and a broad shape to those lines from gas sweeping around at enormous speed. Those signatures were not there. The second suspect is shock waves. When gas slams into gas at high speed, the collision can excite helium, but shocks leave their own fingerprints in the spectrum, and they tend to sweep up and excite the heavy elements around them too. That did not match either. The third is unusual hot stars we already know about. There's a class called Wolf-Rayet stars, stripped, furious, and hot enough to do this. But Wolf-Rayet stars are the late stage of massive stars that were already rich in heavy elements. If that were the answer, the heavy elements would be sitting right there in the data. And this is the point where the case turns. Because the thing that eliminated every one of those suspects is not something the astronomers found. It's something they did not find. In the entire spectrum of that object, there are no metal lines. None. In astronomy, metals mean everything heavier than helium. Carbon, oxygen, nitrogen, iron. And when you point a spectrograph at almost anything in the modern universe, those elements announce themselves. Here, nothing. Just hydrogen and helium. So put the two halves together, because on their own, neither is remarkable. Something is radiating hard enough to strip helium atoms bare. And whatever that something is, it contains no heavy elements at all. Every conventional source of that radiation requires heavy elements to exist in the first place. The signal demands enormous energy. The absence forbids everything that normally supplies it. One thing satisfies both conditions. A cluster of stars made of nothing but hydrogen and helium, burning at temperatures no modern star reaches. Exactly what population 3 was predicted to be, 60 years before anyone could look. And a separate team detected a hydrogen line at the same position, independently, anchoring the identification. The published conclusion is unusually direct for a field that hedges by habit. Population 3 stars are the most plausible explanation, with no satisfactory alternative from any other class of source or mechanism. If that holds, it tells us something we could not learn any other way. How big the first stars actually were. Theory predicted they should be top-heavy, skewed toward the enormous, because pristine gas cannot cool efficiently enough to make small stars. That was a prediction. The strength of this helium signal now supports it with an observation, which is a completely different kind of statement. And there's a detail I keep turning over. This pristine pocket is sitting 3,000 parsecs from a galaxy already loaded with heavy elements, right next door to a place that's moved on. There's a patch of gas that the universe simply never got around to contaminating, still making stars the old way, 400 million years in. A second paper, published alongside the confirmation, takes that further, using this one object to put the first real observational constraints on how the mass of the first stars was distributed. That number matters more than it sounds. It sets how much ionizing light flooded the early universe, and therefore, when the cosmic fog cleared, which elements got made first and in what proportions, and what those stars left behind when they died. Possibly the seed black holes that grew into the supermassive ones sitting at the centers of the galaxies today, including ours. It's also worth saying that Hibby is not the only candidate. Astronomers have flagged others, a system called LAP-1b and a handful of extremely metal-poor objects further along in cosmic time. but almost none of them show the helium signature that makes this one so hard to dismiss. What the field needs now is a second Hebe, found by a different instrument in a different part of the sky. So that's the case. A faint smudge beside a bright galaxy, a signal that demands impossible energy, and an absence that rules out everything capable of producing it, except the one thing nobody had ever seen. It's not yet certainty. The team would be the first to say so, and the confirmation that settles it will take deep observations still. But for the first time, the first stars in the universe may not be purely theoretical. This channel is about exactly these moments, where an absence in the data matters more than anything in it. If you want to be here when the confirmation lands, subscribe and stick around. Until next time, clear skies.